My name is Joseph Azevedo, and this is my lab report for Lab 3. In this report, I'm going to go over the purpose of the lab, the fundamental physics principles involved, the procedure involved and what measurements were taken, the computational model created to aid analysis, and finally the results of the lab, during which I estimated the magnetic dipole moment of my small bar magnet to be 0.202 ampere meters squared, and compared off-axis measurements to results from the computational model to find that they were comparable within a factor of about 43. So, starting off, the purpose of this lab was to explore the properties of magnetic dipoles, and to use observations to estimate the magnetic dipole moment and distance dependence exponent of a small bar magnet. To do this, we're going to rely on a handful of fundamental physics principles, namely, the magnetic field of a magnetic dipole, both on-axis, perpendicular, and off-axis, the concept of distance dependence, the Earth's own magnetic field, and the superposition of magnetic fields. The procedure itself involved the following steps. First, using a magnetometer app on a smartphone, identify the location of the magnetometer sensor and orient it such that the x component of the measured magnetic field is around 0. Then, measure the magnitude of the magnetic field created by an on-axis placement of a small bar magnet at varying distances from the phone. Next, measure the Earth's ambient magnetic field strength. And finally, measure the magnitude of the overall magnetic field when the bar magnet is placed at a 45-degree angle from its previous configuration. Once these steps were performed, I obtained the experimental values as shown in the table. To use these to derive the magnetic dipole moment and distance dependence exponent, I first graphed the natural logarithm of the distance from the magnet and the natural logarithm of the magnetic field's x component. This is important because the strength of the magnetic field created by a magnetic dipole exhibits some distance dependence, in that it varies by some exponent, n, and some coefficient, k, depending on the distance, r. By plotting the natural logarithm of these observed values, we turn our distance dependence form into a linear equation, which allows us to perform least squares regression on the experimental data to find the slope and y-intercept of the line of best fit. These values correspond to n and the natural logarithm of k respectively, which we can use then to calculate the true value of k. Finally, with that, we can use the equation for the magnetic field created by a magnetic dipole to find the magnetic dipole moment mu of the bar magnet. Once this was determined, I then used a programmatic model to visualize the magnetic field around a magnetic dipole and compare the measurements taken for the 45-degree angle configuration to the expected value using the magnetic field equation. With that in mind, I'd like to take a second to walk through the major components of the GlowScript code. First, the script includes physical constants, creates a visualization of the magnetic dipole as a cylinder at the origin, and defines some helper functions. Then it defines 6 different observation locations and calculates the magnetic field created by the magnetic dipole at each location. Finally, it calculates and visualizes the magnetic field at the same location, distance-wise, used during the experiment to find the magnetic field at a 45-degree angle off-axis location. Looking at the results, the magnitude of the magnetic field using the same distance d from the magnet that the computational model predicts is different from the measured magnetic field strength to a factor of about 43. This represents a significant difference between the ideal and experimental values, and likely indicates that our experimental measurements lacked accuracy, potentially due to other ambient magnetic fields present when performing the experiment. Also, to recap, the distance dependence exponent was experimentally estimated to be around negative 4.435, and the magnetic dipole was estimated to be around 0.2016 ampere meters squared. From here, I'd like to answer a couple extension questions. First, if I hadn't oriented my smartphone to compensate for magnetic north, then the first portion of my experiment and its results wouldn't have been able to be used. The first portion of the experiment dictated that we orient the magnetometer to minimize the x component of the magnetometer's reading as much as possible in order to minimize the effect of the Earth's magnetic field in our measurements. If we didn't do that, then our measurements would be the result of both the bar magnet and the Earth's magnetic field, and we wouldn't be able to derive the dipole moment of the bar magnet. Additionally, if we were to stick 2 identical magnets together, end to end, and run the experiment again, we would see that the observed magnetic field strength would have been greater, likely to a factor of 2. This is a result of the superposition of magnetic fields, which states that the net magnetic field at a location is equivalent to the vector sum of all of the individual magnetic fields acting upon that location. In conclusion, in this lab, we explored the properties of magnetic dipoles, and used those observations to estimate the magnetic dipole moment and distance dependence exponent of a small bar magnet. In addition, we used a computational model and compared its predicted values for the strength of a magnetic field in an off-axis configuration to observed experimental values.